Welcome back, everyone. In this video, we move on to another form of continuity called uniform continuity. And to give you an idea of what we're going to be getting at, let's jump back to one of our previous videos where we introduced continuity. And in that video, we proved that the constant function, right? Pick any real number and look at the constant function. So here we have f of x equals c. We proved that this was continuous for all real numbers. And for continuity, of course, you choose some coin around the output of the function. So in this case, just the constant c. So we look at some c coin. And we have to find an a coin that maps into that c coin. Well, it turned out for the constant function, it didn't really matter how big you made the a coin. So we chose just say radius 1. So if you chose any x that was between a minus 1 and a plus 1, the image certainly mapped within c minus epsilon to c plus epsilon because they all map to c, right? Like this was really, really quite nice. Okay, so the point is we're checking out this x minus a business, and we said, we can let the delta be 1. And what's amazing in that case is the delta doesn't even depend on the epsilon we chose. All right, but usually our delta does depend on the epsilon, and usually it even depends on the point A we were talking about. And that's why we, at the time, were write down, well, this delta could depend on epsilon, and it can depend on A. Here, it's just a constant. It doesn't depend at all. Okay, but then we also proved that the identity function was continuous. And in that case, which delta we chose? Well, we said, well, let's just let it be less than epsilon. So this is depending on epsilon, but it still doesn't depend on the point A that we were talking about. Okay, so maybe we could write down a function where depending on the A you choose, the delta that you need could actually change. So I want to start by giving you an example where we can see that happening. So in this example, our function is going to be, well, kind of the next higher up polynomial. We did constants, we did the identity function, f of x equals x. So now we'll do f of x equals x squared. And we're going to view this as a function on the entire real number line, right? That's a reasonable domain for this thing. All right, let's say we wanted to show that f was continuous. Okay, now we've already shown that, right, x is continuous, and so if you multiply two continuous functions, it's continuous. So we know x squared should be continuous. But let's say we wanted to do this from first principles, from the definition. Okay, and I'm going to choose, well, I'll just choose some element a in the real numbers, and I'll choose some epsilon greater than 0. Okay, so our goal is to find some a coin which is going to map into the f of a coin of radius epsilon. Okay, well, here is an idea. So let's say, let's set delta, okay, and this is going to depend on both, this will first depend on epsilon, say. Okay, so say I set it equal to the minimum. Okay, so it's going to be the smaller of two values. It's either going to be 1 or it's going to be epsilon. Okay, so if that's true, okay, and for short, I'll just call this delta. If that's true, or not, it is true, but if it's true that I have some point which is within 1, or within delta rather, then x and a will be within 1 of each other. Okay, because either delta is equal to 1, in which case it's just brutally true, or delta is equal to epsilon, because epsilon was smaller than 1, in which case, well, then this difference is less than epsilon, which is less than 1. Okay, so this is fine. Now, we can use the reverse triangle inequality. Okay, so recall the reverse triangle inequality, which tells you that the absolute value of the difference of the absolute values is bounded by just the absolute value of the difference. Okay, so this is just telling you, right, that the distance between two numbers is always at least as big as the distance between the absolute values of those numbers. All right, so in our case, let's take a look at the absolute value of x minus the absolute value of a. Well, by the reverse triangle inequality, we know that, let's compare here. If I take the absolute value of x minus the absolute value of a, we know that is less than or equal to the absolute value of x minus a. But this is an absolute value, so that's always at least as big as what happens when you get rid of the absolute value. Okay, so this is your reverse triangle inequality, and then this is just because a number is always bounded by its absolute value. And of course, this we know is now less than 1, assuming we've chosen our x and a to be within delta of each other. Okay, but now look at the beginning and the end of this equality, or inequality, and that tells us that the absolute value of x, well, just toss this minus absolute value of a all the way across. This will be less than 1 plus the absolute value of a. Okay, so from here, we get that the absolute value of x, so the absolute value of x plus the absolute value of a is going to be less than, well, I'm just adding another absolute value of a, so this will be 1 plus twice the absolute value of a. All right, so why is that good? Well, remember, since I'm trying to show that f is continuous, I actually need to know what the difference between x squared and a squared is. All right, so if I look at the difference between x squared and a squared, well, let's see here. I can factor x squared minus a squared as x plus a and x minus a, and then I can break up the absolute value. Now the x plus a business, right? We know we can use the triangle inequality, so get rid of the reverse from up above. Oops, the triangle inequality. And we know that the absolute value of x plus a is less than or equal to the absolute value of x plus the absolute value of a. But we have the line up above, which tells us that the absolute value of x plus the absolute value of a is less than 1 plus twice the absolute value of a. All right, so we know that this product is going to be less than 1 plus twice the absolute value of a. And then, well, okay, we still have this absolute value of x minus a, which we know is actually less than delta, and we know that delta is less than or equal to epsilon. So this product will be less than 1 plus twice the absolute value of a times epsilon. And while this isn't exactly epsilon here, by the inspired choice theorem, this is good enough. Right? We have some positive multiple of epsilon. So by the inspired choice theorem, or the Inch theorem, f is continuous at a. Okay, so if we ran this back though and said, well, we don't want to use the inspired choice theorem, right? We would like to actually get this to be less than epsilon. The way we would have solved that problem, okay, so to avoid having to use the Inch theorem, so to avoid Inch, we would set delta of epsilon equal to the minimum of 1, and then over here with the epsilon, we would do epsilon divided by 1 plus twice the absolute value of a. Oops. And the reason why this would work is when we got to this step down here and we said, well, x minus a is less than delta, then I could have replaced this x minus a with the epsilon over 1 plus 2 times the absolute value of a. And then this 1 plus twice the absolute value of a would have canceled, and we'd end up with epsilon. Okay. All right, so what's the point? Well, the point is that the delta I choose, even if I'm hiding it when I use the Inch theorem, but realistically, it seems very much actually to depend on the a that I choose. And that's very different from what happened with the constant function and with the identity function. Okay, well, maybe this was just a bad choice. Okay, maybe there was another way of choosing our delta so that we could have gotten rid of this a. So let's see why. All right, so why does delta always, right, this is for f of x equals x squared, have to depend on a? Okay, so let's assume that it didn't have to depend on a. Okay, and what I'm going to do is I'm going to actually choose a specific epsilon, right? I'm going to let epsilon just equal 1. And I'm going to show that if I change my input points around enough, I can't even guarantee that any delta I choose will get the difference between x squared and a squared to be less than 1. Okay, so let's let epsilon equal 1. And we're going to do this by a little contradiction here. We're going to assume we have delta positive such that if, well, I'll just choose some arbitrary numbers now. If x and y are within delta, then f of x, which is now x squared, and f of y, which is y squared, is going to be less than 1. Okay, so assume we've done this. Okay, and this is for all, right? This is for all x and y in the real numbers. So what happens is I say, well, okay, fine. X squared plus y squared, we break it up just like before. This is going to be x plus y and then times x minus y. And we know that the x minus y is bounded by delta. So this is less than delta times the absolute value of x plus y. And here's where everything is going to go haywire. I know that x and y have to be delta apart. But knowing that x and y are delta apart, at most, right? At most delta apart, knowing that they're at most delta apart puts no restriction on the sum of x and y. So for example, if delta was equal to 0.1, okay, so 1/10, I could let my pair x comma y be 9.99. Let's make it 9.99 and 10. So x and y here are within, well, exactly equal to 0.01 apart, okay, which is certainly less than delta. Okay, but I could also let my x and y be 9999.99 and 10,000. And again, x and y are going to be exactly 0.01 apart, which is still less than delta. And you can't stop me from putting more nines into this. I can just keep doing it over and over again. But when I do it over here, you see the absolute value won't matter because everything's positive. X plus y is 19.99. And here my x plus y is, my goodness, 19,999.99. And I can just make this as big as I want. And so for large enough x and y, delta times the absolute value of x plus y doesn't have to be less than 1, right? Which we know we're supposed to be getting to. So in fact, if I set, right, even if I just set this equal to delta, just to make things easy, and I look at the absolute value of x plus y, I know that there exists, let's see, there exists x and y, such that the absolute value of x plus y times delta, right, which we write that on the next line, such that this times delta is greater than any real number. Okay, just make it greater than any real number. Okay, if I wanted it to be at least 1, right, so say, how could I make this greater than 1? This is greater than 1 if the absolute value of x plus y is greater than 1 over delta. Multiply by delta, you get something greater than 1. Okay, so it turns out, right, like it's just never going to work. No matter what I do, if I just say I have an epsilon, I'm going to pick a delta that only depends on that epsilon, doesn't depend on the x and y that I'm allowed to put in, boom, I'm not going to be able to to show continuity for everything using that one particular delta. So this example that we did up here, we weren't just unlucky, we weren't just doing a poor choice of choosing our delta. You really do have to worry about the A. And just from a geometric point of view, the reason why this is happening is that when we drew the constant function, okay, there's no change whatsoever. When we drew the identity function, well, there's change, but the change is always the same. But when we draw x squared, as you go out farther to the right, the change is getting more and more. It's harder and harder to keep, right? If you pick a little box here, if I use the same width all the time, when I get out here, I'm going to leave the box, right down the middle, right? You can see there it is, leaving the box. Okay, so this is what's happening. Now, what if I restricted the domain? Well, then actually everything can work out. Okay, so let's do a quick example. We can see how important the domain is when we define our function. So I'm actually going to write down, it's the same rule, but it's a different function because we're going to use a different domain. So let's say I take the domain just to be the real numbers between 0 and 3. I'll call that g. But it's still going to be the rule that I take whatever input is and I get x squared. Okay. So again, we're going to choose some epsilon greater than 0. And now I'm just going to set my delta to be epsilon itself. Okay. So if I have some point A inside 0, 3, I want to show that G is continuous at A. All right, well, let me choose any other point in there as well. So if I take 2 points in this interval, 0 to 3, let's just graph it there. Okay, you got 0, you got 3, and I have 2 points. Okay, maybe there's my X, maybe there's my A. How big could they get? Well, each of them can get up to 3. Well, not really including 3, but pretty close to 3. So both X and A could be close to 3. So that tells me that X plus A, and the absolute values don't really mean anything here because everything is going to be positive, but X plus A can get all the way up to, well, almost 6, right? You can get X and A up to almost 3, so X plus A can get up to almost 6. So that tells us that the difference between x squared and a squared, which we again know is the product of the sum of x and a with the difference of x and a in absolute value, and this absolute value of x plus a we know is less than 6, and this x minus a, well, if everything lives between 0 and 3, then x and a can be at most 3 apart, sure, but actually we want to choose them, right, okay, to be less than delta apart. Okay, and delta is epsilon in this case. So that means that this product is less than 6 times epsilon. And now we can use the inspired choice theorem, but you'll notice even at the end here, there's no dependence, right, that we see on the A itself. Okay, so by the inspired choice theorem or the inch theorem, G is continuous at A. Okay, but nothing in here actually, we didn't use the actual value of A other than knowing it lied between 0 and 3. Okay, and this because if we stop looking at our graph at some point, okay, so okay, we'll do there to there. Now, even though this graph eventually will start growing faster, on this interval here, the growth of the function is bounded. It never grows too fast. Okay, this actually gets, this is very much related to something called Lipschitz continuity, which I'm going to let you look up. Okay, so this is all meant to set you up for the definition of uniform continuity, which is essentially going to say that if we want a function to be uniformly continuous, then the delta we choose should not depend on the input point. It should not depend on the A that we're working with. Okay, which means we're not going to be talking about uniform continuity at a point, right? That's just not a thing. Instead, we're going to be talking about uniform continuity on the entire domain. Okay, so we'll finish here with this definition. So f here is going to be some function with domain D, and we're going to say it is uniformly continuous. That's funny. Continuous on D if for all epsilon greater than 0, this just looks like continuity, there exists a delta, right, which I'm going to write explicitly, depends on epsilon, it's not depending on the A, greater than 0, such that if x and y are any elements in D, okay, any elements and x and y are bounded, right, by delta, the difference between x and y is bounded by delta of epsilon. It does not depend at all on what your x and y are. Then the images, the f images of x and y are bounded by epsilon, right? The distance between them is bounded by epsilon, okay? So let's just quickly go back and look at our definition of continuous functions. Okay, it's going to look almost the same. Oops. We said for all epsilon greater than 0, there exists a delta which depends on epsilon, but also on the A we're talking about typically. Okay, such that if x is in D and x and A are within delta, then f of x and f of A are within epsilon. It looks almost identical. Okay, the only difference here is when we defined continuity, right, it was at a point, right, we said it's continuous at A. And so this delta depends on the A that we're choosing, right, at least in a vacuum. For specific examples, of course, we know it doesn't have to. Okay, and so we now know already, right, what do we know? Constant function and the identity function are uniformly continuous on the real numbers. F of x equals x squared on the real numbers is not. But g of x equals x squared on the interval 0, 3 is uniformly continuous. Okay. All right, so next time we will do, hey, you guessed it, a sequential characterization of uniform continuity. All right, we'll see you next time.